Hey, welcome back. Now let's discuss how a pi bond is formed. Okay, in the last class we discussed about the formation of sigma bond. Now we want to discuss the formation of pi bond. So a pi bond is actually formed by the lateral overlap between orbitals across or perpendicular to internuclear axis. Okay, so as discussed in the last class, let this be the internuclear axis. Internuclear axis, which means your z axis. Internuclear axis, z axis. Okay, if there are two px orbitals, okay, our convention is that this is z axis, y axis, x axis. Okay, so two px orbitals. If we have two px orbital like this, when they get overlapped, usually the overlapping shown like this, or this is very similar to that. Like this. Okay, this is how they overlap side to side. Ready? And this overlapping, relatively the extent of overlapping is comparatively lesser. Extent of overlapping will be lesser as that of end-to-end overlapping. We know that end-to-end overlapping, which is discussed in the last class, that is a form which leads to the formation of sigma bond, have greater extent of overlapping. So that will be a strong bond. Here, relatively lesser extent. Okay. So if the overlapping is between two px orbital, or if the overlapping between two px, these are two py orbitals. Okay, these are two py orbitals. When these two py orbitals are overlapped, there is a chance for side to side overlap to form pi bond. Okay, or if we consider z axis here and x axis here, so this is a px orbital. This is not inclined at a 45 degree. Okay, you know the actual figure. This lob to here and this one to the beyond the plane. Okay, here, which is on the back side. Okay, so these are the two lobes. So these are two px orbital. So when they overlap, there also a chance for the overlapping or the chance for the formation of pi bond. Okay, so between two px or between two py, usually there is a chance for the formation of pi bonds. Okay, pi bonds. Ready? Fine. So this is how a pi bond is formed. Okay, so let me explain pi bonds using an example. For example, if I have a molecule nitrogen, we know that there is two nitrogen atoms. The first one is 1s2, 2s2, 2px1. Let me show that in orbital sense. 2px, 2py, 2pz, 2px1, 2py1, 2pz1. And what about the next nitrogen? The second nitrogen is also 1s2, 2s2, 2px, 2py, 2pz. Okay, and they all are in this pattern. Okay, fine. Ready? When they combine, what happens? There is a chance for px overlapping like this. Before that, the first chance is between these two pz. These two pz brings the sigma bond. You know, when two pz and two pz get overlapped to form sigma bond, and chance for two px overlap to form pi bond. There is a half-filled oppositely spinned px orbitals. Half-filled oppositely pinned two px orbitals. So when they get overlapped, they forms a pi bond. Half-filled oppositely spinned pz overlapped. They get overlapped on end-to-end patterns. So they forms a sigma bond, and there is a chance for py overlap also. So which leads to the formation of a pi bond. Okay. So it is clear that there is chance for 3 bonds in your nitrogen. Okay, And the first one, that is a sigma, and the rest are pi. The rest are pi. Okay. So let me show one more example, that is the overlapping in or the bond formation in oxygen molecule. In your oxygen molecule. Okay. What about the electronic configuration of oxygen? Electronic configuration of oxygen, that is, we have in your O2, we have two oxygen. Configuration 1s2, 2s2. What about the valence orbital? The valence orbital is 2p4. 2p4 is like this. And here 1s2, 2s2, 2p4. And here the 2p4 is like this. So let this be the py and this be the pz. Py, pz. So there is a chance for the first bond between two pz. PZ, PZ overlapping to form a sigma bond. And the second PY, PY overlapping to form the pi bond. Okay, ready. So actually it is clear that in case of your oxygen, there is actually a sigma bond and the next bond is a pi bond. So it is clear that if you consider the previous example, or the examples which we discussed in the last part, HH, FH or HF, FF, where these all bonds are sigma bond, right? So if there is a single bond, then it will be a sigma bond. If there is a multiple bond, then one is sigma, the next is pi. If there is a multiple bond, one is sigma and others are pi. Ready? I think the point is okay, and moreover the formation of pi bond is also okay. It is formation of delta bond. So usually when there are two dz square orbitals, the bond overlapping between them forms a bond of sigma bond. If the internuclear axis is z axis, or if there is dxz overlapping between two dxz or two yz orbitals, and there forms pi bond. Okay. Or if there is an overlapping between two dx square minus y square orbitals, dx square minus y square orbitals of two atoms, or dxy orbitals of two atoms, then there is a chance for the formation of delta bond. For example, let me show this one. If this is an internuclear axis, z axis, then this is the dx square minus y square orbital, right? And this is how a delta bond formed. A delta bond formed between two dxy. So this is a dxy, dx square minus y square, not dxy. And this also dx square minus y square. Okay, which is along the internuclear z axis. And the overlapping between them is said to be what? Which leads to the formation of delta bond. Okay, ready? Fine. So the next concept. So let me compare the sigma bond with pi bond. Okay, question may ask like that also. There may be some statement-wise questions since this is a theoretical chapter. So comparison between your sigma bond and pi bond. These are the two different types of bond which are usually in our discussion. Okay, delta bond is which are discussed in a rare pattern. Okay, so sigma bond and pi bonds are important, and this is only bonds which are discussed in your Ncert textbook. Okay, so sigma bond. What about sigma bond? Which is formed by, write the point, formed by the axial overlapping across internuclear axis. Axial overlapping of orbitals across internuclear axis. We know that. This overlapping is across internuclear axis, right? Yes. What is that internuclear axis? Across that internuclear axis, we obtain the sigma bond. Okay, so this overlapping is axial overlapping across the internuclear axis. Here, this is a lateral overlapping, which is perpendicular to internuclear axis, right? In your lateral overlapping, what is the specialty? The orbitals are perpendicular to internuclear axis and they get overlapped. Okay, perpendicular to internuclear axis. The next point is about its electron density. We know that the overlapped orbitals in case of your sigma bonds, the overlapped orbital which is in across internuclear axis, right? Which covers the internuclear axis, which is symmetrical around the internuclear axis. So electron density is actually in this overlapped area, right? We can see the electron density in this overlapped area. So electron density is cylindrically distributed around our internuclear axis. So the next point, electron density is cylindrically distributed around internuclear axis. What about here? Here the overlapping is on the top and bottom position. So what is the speciality means? There is an overlapping in the top position and bottom position. So there is a formation of electron density on a upper plane and on a lower plane. Okay. So here the electron density around cylindrically distributed around internuclear axis. Here the point, electron density in two planes parallel to internuclear axis. The overlapping orbitals are perpendicular to internuclear axis, but the electron density which occur in two planes which are parallel to the internuclear axis. Ready? Electron density which are parallel to two planes which are parallel to internuclear axis. Okay. Next point. Overlapping also known as axial overlapping, end-to-end overlapping, head-on overlapping. Okay. Here overlapping also known as lateral overlapping or sidewise overlapping. Lateral overlapping or sideways overlapping. Okay. What is the specialty here? Here the greater extent of overlapping, right? The two orbitals means the overlapping is in a greater extent because they overlapped in a maximum distance, right? Which means they can cover a maximum distance by means of overlapping. But here it is relatively lesser extent of overlapping. Okay. So greater extent of overlapping hence strong bond. We know that we already discussed the features of atomic orbital overlapping. Whatever be the extent of overlapping, that much is the strength of the bond. Here the greater extent of overlapping, so a stronger bond. Here relatively lesser extent of overlapping. Relatively means that sense is in comparison with your sigma bond. So relatively lesser extent of overlapping. Relatively lesser extent of overlapping. Okay. So lesser extent of overlapping. What happened? Weak bond. Okay. And we already seen that if there is a single bond, that's a sigma bond. If there is a pi bond, one is sigma, then others are pi. So pi bond can't exist independently, right? Okay. So can exist independently. Sigma bond can exist independently if there is a sigma bond. Single bond, that is a sigma bond. So sigma bond can exist independently. But if there is a multiple bond, then one sigma, others are pi, which means pi bond may form if sigma bond is formed first. Okay. So can exist independently, cannot exist independently. Ready? Free rotation of bond possible here. In case of your sigma bond, the free rotation of bond is possible. Okay, because electron density is cylindrically distributed in the nuclear axis, around internuclear axis. That's why they can show conformational isomerism. Alkanes are showing conformational isomerism because bond rotation possible. Next, in case of pi bond, free rotation not possible. Okay, that's why alkenes are showing what? Geometrical isomers. Okay. The next point. Hybrid orbital can form sigma bond. hybrid orbitals can form what? Sigma bond. Here, always unhybrid or pure atomic orbital can form sigma bond. Okay, pi bond. Actually, sigma bond can be formed by between the overlapping between two atomic orbital or hybrid orbital or atomic orbital and hybrid orbital. Ready? We will discuss the overlapping of hybrid orbital, right? Wait. But the pi bond, which is only formed by the overlapping between two atomic orbital. Hybrid orbitals never form the pi bond. Okay? Keep it in mind. So these are the difference between what? Sigma bond and pi bond. Okay? Ready? And that's all about the atomic orbital overlapping. One more idea is there are different types of overlap based on wave function of orbital. Based on wave function of orbital, we know that orbitals, atomic orbitals means atomic orbital represents psi is the atomic orbital which represents the electron wave. Okay, so every electron wave have a positive crest and negative trough, right? So if I have a orbital like this, if I have a p orbital like this, and this analogous to the positive crest, this is a positive lobe which is analogous to the positive crest, and negative lobe which is analogous to the negative crest. Okay, ready? But in case of s orbital, usually s orbital is represented either as positive or as negative since the shape is symmetrical. But in case of p orbital like that, there is exactly two different area. If this is a positive one, this is a negative one. If this is a positive one, this is the negative one. With respect to origin, there is two different area. So these two are designated like this: positive or negative, which is analogous to the crest or trough of the electron wave. But with respect to the origin, there is actually a symmetrical figure is your s orbital. So that's why either they are represented as positive or they are represented as negative. Okay. So based on this sign convention, the overlapping may be three different types. It's very easy. That is a positive overlap. Positive overlap means overlapping between two similar one. Okay. For example, let s orbital have a positive designation. If this is overlapped with a p orbital with the positive lobe like this, so this represents a positive overlap. Okay. Similarly, what will be the negative overlap of this category? If the very same s orbital have a positive designation, if this is overlapped with your negative orbital, this is overlapped with the negative orbital. Okay, negative orbital of p orbital. So this is represented as negative overlap. So s with the negative lobe. Okay. The next we have the orbital overlapping of pz's, right? Pz. If the positive lobe of pz overlapped with the positive lobe of another pz, then that is a positive overlap. Or it may be if the overlapping is made with the like this also, negative lobe of one with the negative of another, that also brings the positive overlap. But if the very same pz overlapping is like this, positive of one with the negative of another, then that is a negative overlap. Okay, so if the overlapping between two oppositely designated orbitals, then that is a negative overlap. With a similar orbitals, then that is a positive overlap. Okay, and this is also found in your what? Lateral overlapping also. So this is px and this is also px. Okay, this is s and this is a pz. S, pz, 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 pz. So let this be the px or py, py. So this is the positive lobe, negative lobe, positive lobe, negative lobe. If the overlapping is like this, then that belongs to positive overlap. Okay. Or if the bond is formed by the overlapping of orbitals with a designation like this, then that belongs to negative overlap. I think you may get an idea about the positive negative overlap. Okay. Sometimes a question may ask like that also. Okay. I think it is discussed in the textbook. Ncert. Ready? So there is one more category, zero overlap. Zero overlap. Due to this formation of zero overlap is due to the improper orientation. Zero overlap formed by the improper orientation of orbital. Formed by the improper orientation of orbitals. If the orbitals are in improper orientation, then we obtain a zero overlap. And what is the effect of the zero overlap? Means there is no bond formed. No bond formed due to the zero overlap. But if positive or negative overlap, whatever be the category, positive or negative overlap, there forms a bond, either sigma bond or pi bond. Okay. What about the category of zero overlap? If I have an s orbital like this and a px orbital like this, okay, so they never get overlapped because there is no proper orientation. If I have a px orbital like this and pz orbital like this, they also won't overlap because px orbital means one orbit is like this. This is a py orbital, sorry. This is the px orbital. Px orbital means another orbital is like this. One lobe is to here, another to the back. So they never get overlap because one is like this and one is like this. One is like this and one is like this. They never get overlapped. Here, one is a spherical one, another one is like this. They never get overlapped. But this is pz, they can overlap by means of sigma bond. Okay, so spx or between s and px or s and py, zero overlap will be there, or between px and py. Okay, fine. So that's all about the different types of overlapping based on the verb function of orbital or the designation, like the designations corresponding to the crest and trough, like plus and minus. Okay, fine. The next idea, that is, in order to, now we explained how a bond is formed. Either it is, the bonds are formed by, either formed by the overlapping between two orbitals, right? So in order to form a bond, there will be overlapping of orbital, okay? But we can explain the bond formation by this type of overlapping, like SS, SP, PZ, PZ, PX, PX, PY, PY, like that. We can only explain the bond formation of diatomic molecule, right? We only explained the bond formation of diatomic molecule by the overlapping between two atomic orbitals. But we know that there is plenty of polyatomic molecule with a well-defined geometry. We already discussed or drew the geometry of all category, right? Linear, like that, okay? Linear, triangle, planar, tetrahedral, like that. So we want to explain how that particular geometries are formed. Moreover, how the bonds are formed in polyatomic molecule. Okay, so in order to consider the very same bond formation idea in polyatomic molecule and to explain how the geometries of polyatomic molecules are formed, we require the second objective of valence bond theory, that is hybridization. What is hybridization? Hybridization, which is explained by Linus Pauling. So for what you need hybridization means, in order to explain the geometry of polyatomic molecule, how a polyatomic molecule have a specific geometry like linear, triangle, planar, tetrahedral, like that, or to explain how bonds are formed in polyatomic molecule. Okay. So the purpose of hybridization here is to explain how geometry possible. Moreover, to explain how bond formed in polyatomic molecule. How bond formed in polyatomic molecule. How the bonds are formed in polyatomic molecule. These are the two main ideas. Okay. For that, you have to know hybridization, which is introduced by the Linus Pauling. And what is mean by hybridization means? Hybridization is a intermixing. That's a phenomenon of intermixing of orbital. Your pure atomic orbitals get intermixed to form a set of new orbitals with the same shape and same energy. Okay, you have different type of orbitals with the similar energy, only the similar energy. For example, I have s orbital, p orbital. The shape is not same. We know one is spherical, one is dumbbell, but they have nearly same energy because s orbital is from 2s and p orbital is from 2p. Okay. So if you have number of atomic orbitals with a similar energy, in order to form a bond in polyatomic molecule, for example, in order to form a tetrahedral 4 bonds in methane, what happens here is your central carbon atom, which try to intermix its pure atomic orbitals of similar energy and make a new set of atomic orbitals. That the new set of atomic orbital formed is called the hybrid orbitals. And what is the specialty of that hybrid orbital means? The hybrid orbitals are arranged in space so that they can produce a particular geometry. Okay. So actually here 4 sp3 hybrid orbitals of carbon brings the 4 sp3 hybrid orbitals of carbon brings the tetrahedral geometry actually. In order to form the 4 sp3 hybrid orbital, they are actually mixed. They are actually intermixed for atomic orbital, for pure atomic orbital like s, px, py, pz. Okay, so fine. So this is the idea of what hybridization. Okay, so let's write some features of hybridization. Before that, you have to define what is hybridization. Hybridization is the intermixing of atomic orbitals of similar energy. Intermixing of atomic orbitals of similar energy to form a set of new orbitals. To form a set of new orbitals. To form a set of new orbitals with the same energy and same shape. To form a set of new orbital in bracket hybrid orbitals, close the bracket, with the same energy and shape. With the same energy and shape. Okay, so that's a phenomenon of intermixing of atomic orbitals of similar energy to form a set of new orbital. Where the formed set of orbitals are called hybrid orbitals. So where the hybrid orbitals have same shape and same energy. Ready? Fine. Features of hybridization. What about the nature of atomic orbitals that are intermixing? We know that pure atomic orbitals are intermixing here. And we know atomic orbital have 3 different possibilities. Either the atomic orbital vacant, or the atomic orbital is unpaired, or the atomic orbital is paired. Whatever be the nature of atomic orbital, or every atomic orbitals can intermix here. Here vacant atomic orbitals can intermix. Unpaired electron orbital with half-filled orbital can intermix. Fully filled orbitals also can intermix. Okay, so that is the first feature. Atomic orbitals of vacant, half-filled or fully filled can participate in hybridization. Intermix means they can participate in hybridization. Okay, atomic orbitals of vacant, half-filled, fully filled can participate in hybridization. If the hybrid orbital is from a vacant orbital, then that is a coordinate bond. Or in that orbital forms a coordinate bond. If a half-filled orbital participate in the hybridization, then that will be a bond, covalent bond. That will be a covalent bond. If that's a general idea. Okay. If a paired orbital which participate in hybridization, then that will be a lone pair. That will be a lone pair. So the three different varieties like vacant, half-filled, or fully filled orbitals can participate in hybridization. The second point, okay, number of hybrid orbitals will be equal to the number of hybrid orbitals will be equal to the number of hybrid orbitals formed will be equal to the number of atomic orbitals intermixed. Number of hybrid orbitals formed will be equal to the number of atomic orbitals intermixed. For example, if the intermixing is between S and P, then there forms sp hybrid orbitals. 2 sp hybrid orbitals. If the intermixing is between S and P, which means 3 orbitals, then there forms 3 sp2 orbitals. Okay. So how much number of atomic orbitals are intermixed, that much hybrid orbitals are formed. Okay. The third point, that is hybrid orbitals are arranged in space. Hybrid orbitals are arranged, each hybrid orbitals, right, like that. Each hybrid orbitals are arranged in space to bring a shape of polyatomic molecule. Okay, to bring the shape of polyatomic molecule. That is the third postulate. The fourth postulate, each hybrid orbital have a positive longer lobe and negative smaller lobe. This is the shape of hybrid orbital. Each hybrid orbital have a positive longer orbital, and negative smaller orbital. Okay, this is a positive one and this is a negative one, and this is the overlapping orbital. Okay, so this is the overlapping end. If this is overlapping end, then if this one is the greater overlapping with the overlapping one with the maximum size, means it can produce greater extent of overlapping so that the bond will be stronger. Okay. So the next point, this is how the shape of hybrid orbital. Next point, since the overlapping end have greater extent or greater size, since the overlapping end have greater size, comma, greater extent of overlapping, and more stronger the bond. So a bond formed by the overlapping of hybrid orbital involving hybrid orbital will be more stronger than the overlapping between atomic orbital. Okay, fine. Ready. So number 5, fifth point. Promotion of electron is not a necessary condition for hybridization. Promotion of electron is not a necessary condition for hybridization. Okay, copy that word. I'll explain what is that. What does it mean? Okay, when I'm explaining the hybridization. Promotion of electron is not a necessary condition for hybridization. Okay. Next point is, since hybrid orbitals are longer, they can provide more directional bond than overlapping between atomic orbital. Since hybrid orbital are longer, they can provide more directional bond comparing to the overlapping by atomic orbital. Okay, we already discussed the overlapping of two atomic orbitals. And what is the direction property of that typical bond in overlap, which formed by the overlapping of atomic orbital? Where if the bond is formed by the overlapping of atomic orbital, it have more direction property than the previous one. Okay, which means hybrid orbital overlapped bond have more directional property than the bond formed by atomic orbital overlapping. Okay, and order of directional property, we'll discuss nearly 5 different, nearly some kind of hybrid orbitals like sp, sp2, sp3, sp3d, sp3d3, sorry, sp3d2, sp3d3. Okay, we will discuss about this. Okay, so 1, 2, 3, 4. There are 6 different types of hybrid orbitals. sp between two s and p, sp2 between s and 2p, sp3 between s and 3p, sp2 between s and 3p and d, sp3d2 between s and 3p and 2d, sp3d3 between s and 3p's and 3d's. So what is the directional property, or what is the directional property of these different types of hybrid orbital means? That will be like this. Okay, so the direction property of hybrid orbitals, which is much greater than atomic orbitals. Okay, so if the overlapping is between atomic orbital, then the direction property is that direction property of that particular orbital overlapping is less than the corresponding hybrid orbital overlapping, and the hybrid orbital overlapping follows this order. Okay, next point. A single element can form different types of hybridization. For example, we know that in alkane carbon forms sp3 hybridization, or in alkene carbon forms sp2 hybridization, or in alkyne carbon forms sp hybridization. Okay, a single element can form different types of hybridization. That depends on experimental condition. Okay, that depends on the condition of the formation of that molecule. The surrounding condition leads to the formation of that molecule. Okay. Last point, overlapping involved in hybridization. Overlapping involving hybrid orbital. Okay, hybrid orbitals are ready for overlapping, right? Overlapping involving hybrid orbitals can only form sigma bonds. Okay, so if there is an overlapping between hybrid orbitals or involving hybrid orbitals, the bond formed will be sigma bond, no doubt. Okay. So these are the different features of hybridization. Okay, keep it in mind. So there is no need to produce these all statements in your exam paper. You have to know what are the ideas. Okay, you simply go through this. Okay, then answer some questions from this one. Then it will be okay. Okay, no need to by heart this one. Okay, so you have to know a hybrid orbital have a greater overlapping orbital, 2 lobe. Hybrid orbital have 2 lobe. One is a greater size, one with a greater size, another with a small size. Okay, the greater size overlapped orbital lobes are usually ready for overlapping. That's why there forms a strong bond. So you have to know all these ideas. Ready? Then only you can do the questions. Ready? No need to by heart. Fine. So you just go through the whole once or twice and answer the questions. Okay, fine. So we can discuss the different types of hybridization using examples like sp, sp2, sp3, sp3d in the next part. Okay.